Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss work done in an isothermal process, work done in an adiabatic process, and finally the limitations of first law of thermodynamics. Let's begin. First, work done in an isothermal process. Isothermal process means in that of process the temperature remains constant. That indicates the change of temperature is 0. To calculate the work done in an isothermal process, let us consider 1 mole of an ideal gas that enclosed in a cylinder. 1 mole of ideal gas is enclosed in a cylinder and that cylinder having perfectly non-conducting walls. These walls are perfectly non-conducting. And conducting bottoms. Look here, the walls of this cylinder, walls are perfectly non-conducting walls, non-conducting walls, and the bottoms, that portion is perfectly conducting, that is conducting wall. The cylinder is fitted with a perfectly non-conducting, frictionless and weightless piston, that is fitted with non-conducting, frictionless and weightless piston. See the piston, that piston is also what? Non-conducting. Here we consider 1 mole of ideal gas. 1 mole of ideal gas. Let P be the pressure, V be the volume, T be the temperature of that gas. Let the area of cross section of piston, area of cross section of piston is equal to A, and let we assume that gas expands isothermally and piston moves upward through a small distance dx. That piston moves upward with a small distance, that distance be dx. What we write? Let the gas expands isothermally and piston moves upward through a small distance dx. through a small distance dx. Okay. So, what should be the work done by that gas? Since the piston moves upward, what should be the work done by that gas? Then work done by the gas the small work done dW is equal to force into distance, or dW is equal to F dot dx. Here cos theta, that the angle is 0 degree, cos 0 is equal to 1, so F dx. Instead of force, we can write pressure is equal to force by area. So, force will be pressure into area. In place of force, we can substitute pressure into area. So, dW is equal to PA dx. Look here, A is the area and dx is the displacement. So, A dx gives rise the change in volume, or what the increase in volume. So, dW is equal to P dV. Here dV is equal to A dx, area into small displacement, that is increase in volume. Now, this is the small work done when that gas moves upward. What should be the total work done? Means we have to integrate. Let we choose first. In initial condition, let the pressure and volume will be P1 and V1, and at final position the pressure and volume change to P2 and V2. So, the total work done during isothermal expansion when gas moves from initial position, from initial state. Let in that of initial state, it will be at point A and its pressure will be P1 and volume will be V1, to final state, let that final state be point B, where the pressure change to P2 and volume change to V2. Here let I prefer that is A point, initial point, here the final point B. So, here the total work done, that is W, is equal to integration dW from 0 to W is equal to integration from, in place of dW I substitute P dV. Here volume change from V1 to V2, that for W. Now, I can use here from gas equation, PV is equal to RT. Here N will be 1 since we consider 1 mole of gas. PV is equal to nRT. So in place of N I substitute 1. PV is equal to RT. In place of P, that is RT divided by V. In place of P we write RT divided by V is equal to integration from V1 to V2, that is RT divided by V dV W. R, that is universal gas constant. Here T, since we consider isothermal process, T is constant, the constant to that of outside. So RT to outside, that is dV by V, integration from V1 to V2, total work done W. Or W is equal to RT dV by V, integration of dV by V, that is ln V from V1 to V2. We take upper limit minus lower limit. So W is equal to RT ln V2 minus ln V1. W is equal to RT ln A minus ln B, that is ln A by B, sorry V2 by V1, V2 by V1, V2 by V1. And that ln, when I change to that of log, it will be 2.3026 RT, that will be log of base E V2 by V1. That is the expression for that of work done in case of isothermal process. That is the expression, this is the expression for work done in an isothermal process, Since we consider isothermal process, that equation can further be written as in isothermal process. In isothermal process, you know P1 V1 is equal to P2 V2, means the product of pressure and volume will be constant. So final state, the pressure and volume is same as that of, sorry, initial state pressure and volume is same as that of final state pressure and volume. Here V2 by V1, V2 by V1 written as P1 by P2. Just substitute that in this equation, that is equation number 1. So equation 1 becomes total work done W 2.3026 RT log base E P1 by P2, P1 by P2. That is the expression for work done. That is the expression for work done in terms of pressure, That is one expression in terms of volume, that is one expression in terms of pressure. This is the work done in an isothermal process. Next one, work done in an adiabatic process. Similar procedure we have to take to calculate the work done in an adiabatic process. Same thing, but just simply change in adiabatic process the heat is constant. means the change in heat will be 0. So, let us consider 1 mole of an ideal gas. We consider here 1 mole of an ideal gas in a cylinder having perfectly insulated wall. All the walls are perfectly insulated and also the bottom, but in previous one the bottom is not non-conducting wall, that is conducting wall, but here all the walls are non-conducting. Again the piston which is fitted to that of cylinder, that also non-conducting. All sections, this wall, that wall and the piston, all these are non-conducting. Non-conducting means throughout the entire process the heat will be constant. Here we consider 1 mole of ideal gas, 1 mole of ideal gas. So, all the parameters are same also in that of case, means let we take for pressure P, volume V, temperature will be T, and let the piston moves upward and the gas expands. Since no heat enters or leaves the system, hence that one is an adiabatic expansion of gas. So, what we have, since the expansion of gas is adiabatic, again let that piston moves this position which is at a distance of dx, and the area of the cross section of that piston will be A, same thing. So, what happened according to first law of thermodynamics, the amount of heat supplied is used in change in internal energy plus some work done. Since the process is adiabatic, so dq will be 0, that means 0 du plus dw, as dq is equal to 0 since it is adiabatic, process, dq is 0. Here dq, that is the amount of heat supplied to that of gas, du is the increase in internal energy of gas, dw that is the work done in adiabatic process against that of external pressure. Here dw is equal to minus of du. In place of du we can write, we know Cv, that is specific heat of gas at constant volume, Cv that is du by dt at constant volume. So, du is equal to Cv dt, in place of du I substitute Cv dt, dw is equal to minus Cv dt. Here Cv is the specific heat of gas at constant volume and dT is the change in temperature, that is the change in temperature. This is the small work done when that piston expands to a distance of dx. What should be the total work done? In the total work done, when gas expands adiabatically from temperature T1 to T2. Total work done W, integration from dW from 0 to W, or total work done W is equal to integration from Cv dt, that is minus Cv dt from T1 to T2, the temperature change from T1 to T2, T1 with the initial temperature and T2 with the final temperature. So, Cv here W is equal to minus Cv is the constant to that of outside. So, integration of dt, that is T from T1 to T2 using upper limit and lower limit. W is equal to, that is T2 minus T1, but minus multiplied to that of bracket, it will be Cv T1 minus T2. Okay. But we know here we take it an equation. Okay. But we know that Cp minus Cv is equal to R. It is specific heat of gas at constant pressure, it is the specific heat of gas at constant volume. R is the universal gas constant for that of 1 mole of gas. Now, dividing Cv on both sides, that is Cp by Cv minus Cv by Cv, R by Cv. Cp by Cv, that is the gamma, minus Cv by Cv is equal to 1 R by Cv, Now, Cv is equal to R divided by gamma minus 1, In place of Cv, I substitute R divided by gamma minus 1. So, work done W is equal to R divided by gamma minus 1 T1 minus T2, that is the expression for work done, during an adiabatic process, Now, if we consider P1 and V1 are the initial pressure and volume of that of gas, let P1 be the initial pressure, V1 is the initial volume, here P2 be the final pressure, V2 be the final volume of that of gas. So, from gas equation we have P1 V1 is equal to RT1, R is the universal gas constant, that is constant for that. Again P2 V2 is equal to RT2. Now, let equation II, subtracting this to that. Now, subtracting that equation, subtracting 2 from 1, we get the RT1 minus RT2, RT1 minus RT2 is equal to P1 V1 minus P2 V2. Here R taking common, that is T1 minus T2 is equal to P1 V1 minus P2 V2. R T1 minus T2 is equal to P1 V1 minus P2 V2. So here in place of R T1 minus T2 I can substitute that one. So let that equation be equation number 3. That equation be equation number 3. So equation 3 becomes, so equation 3 becomes W is equal to, work done W is equal to, in place of R T1 minus T2 I substitute P1 V1 minus P2 V2. So 1 by gamma minus 1 P1 V1 minus P2 V2. That is the another expression for work done in case of adiabatic process. Now here we know what is the work done in an adiabatic process. Finally, we discuss some limitations of first law of thermodynamics. Limitations of first law of thermodynamics. Limitations of first law of thermodynamics. What is first law of thermodynamics? First law of thermodynamics gives an equivalence between heat and mechanical energy. That is, the relation between heat and mechanical energy can be easily understood throughout that of first law of thermodynamics. And according to first law of thermodynamics, heat can convert it into mechanical energy and vice versa. Heat can convert it into mechanical energy and mechanical energy can also be converted into heat energy. But this law fails to explain certain experimentally observed facts. What are the experimentally observed facts that can't explain the first law of thermodynamics? First one, it does not tell us under which conditions heat will be converted, under which conditions heat will be converted into mechanical energy. Under what condition heat will be converted into mechanical energy. That is the first drawback or limitation of first law of thermodynamics, means it can't explain. Next one, it does not tell us about, the direction of transfer of heat, the direction of transfer of heat from one body to another, means why heat does not flow from cold body to hot body. That does not explain about the about the direction of transfer of heat from one body to another, means it can't explain why heat flow from hot body to cold body, but why not from cold body to hot body. Third drawback, it gives no indication, why whole of heat energy can't be converted into mechanical energy, means we know dq is equal to du plus dw, means some amount of heat is used to change in internal energy. That means almost all the heat can't change to mechanical energy. It does not give the indication why whole of heat energy can convert it into mechanical energy. These three are the drawbacks, or we can say the limitations of first law of thermodynamics. So, with the help of this visual lecture, we understand what is the work done in an isothermal process. This is the work done in an isothermal process. This is the expression for work done in an isothermal process in terms of volume, that is in terms of pressure. Work done in an adiabatic process is the expression for work done during an adiabatic process, that is also the expression for work done in an adiabatic process. Finally, the limitations of first law of thermodynamics. These are the limitations of or we can say the drawbacks of first law of thermodynamics. So, with this useful and informative notes, let me wind up this session. Thank you.